lecture, we are going to talk about the optimal control, how we can formulate these kind of problems, and maybe more importantly, how these kind of problems can be solved. In the previous lectures, you have learned how to, let's say, define the dynamical systems, single input, single output systems, multi-input, multi-input systems. But the main focus of this lecture will be to be able to provide a control law that gives the best performance under certain circumstances. It's because of that maybe it makes sense to first start with a definition of optimal control. An informal definition could be done as the optimal control deals with finding a control law that optimizes a certain criteria. So this optimization can be interpreted as minimization of a thing or maximization of a thing. So for example, minimizing the energy consumption or minimizing the required time to execute any task, or maximization of the yield, and so on and so on. And yeah, this control law should be able to provide an optimality the criterion. Okay. And this most of the times means minimizing a thing or maximization of a thing. In various fields of engineering, we have several problems that fits into the scope of optimal control. And I'm going to give you a motivational example to get a better understanding about the problems that we may face in this field. So let's consider a batch reactor that's sketched here, and this means that the compounds A and B is resulting in the final product C. And of course, there are several environmental conditions that leads to the efficiency of this reaction. For example, the temperature of this reactor, and this temperature can be accepted as a control input. So because we can manipulate the temperature, so let's indicate this with the U T. And of course, we would like to evaluate the reaction performance, and this, for example, can be shown itself as the yield rate. And let's say YT is the, let's say, yield in this case, temperature. Okay, fine. So all in all, we have a control variable, which is temperature, to hopefully change the yield rate at the end of the day. And what one can do as a starting point is that let's assume that we apply a constant temperature rate, which is shown as this. Okay, this is time, this is temperature. And as you can see, in this case, we are applying a constant temperature to the reactor and observing the output. And this output, something like that, starting from, let's say, 0 to somewhere like this. And here the x-axis are, this is again time, and this is the yield. So as you can see, our yield increases by time and reaches a certain point at the end, which is this one. But of course, if possible, it's better to increase this yield rate to a higher value. And when we don't have any extra information regarding with the background or principles of a systems, what we can do is the basic approach is the trial and error approach. So let's consider in the second case, we are not applying a constant temperature rate, but a linearly increasing one. So in T, this is again temperature. And this time, the temperature increases constantly. And when we made this, we are observing a different yield rate and maybe yield curve, something like that. Yes, that's relatively better than the previous one, but how can we know that this provides us the best performance? Of course, we are not able to, let's say this is the best performance under some circumstances. And before going into the details of the optimal control, let's assume that for this specific case, we have a temperature curve like that as an optimal value. Okay, So as you can imagine, predicting this curve without having any extra knowledge on the background is quite a hard task. And let's say that the outcome of this one is something like that. Okay, as you can imagine, the optimal yield curve is significantly higher than the rest of the initial tries. Okay, so in this lecture, we are going to learn how we can get this curve if it's possible. But most of the time, in terms of engineering, it's not directly possible to get this analytical optimal solution, or let's say global optimal solution in all cases. It's because of that, in terms of engineering, it may also be sufficient to get curves, or let's say piecewise linear curves, that is close enough to the optimal one. What I mean is that something like that. So most of the time, this dotted piecewise linear curves also provides a significantly well performance, and for example, they end up in a yield curve, something like that. Okay, as you can see, this is not directly fitting the best performance, but it's close enough most of the time in terms of practical conditions. Okay, so in this lecture, we are going to dig deeper on the problem formulation so that we can set the optimal control problem, and at the end, we can get the control law that gives us the best temperature input curve that yields in the best yield value here. So it's because of that, of course, we need to know something on the background. The first thing that I could say at this moment is that we need a mathematical model of our system, how this reaction is happening, and most of the time these can be formulated as mathematical equations like ordinary differential equations or partial differential equations or algebraic equations and so on. The other thing that we need to know is, for example, in terms of my input, what is the boundary values? So there is a practical limit that I can apply a control law. For example, I couldn't apply too much temperature or too much heat, or there could also be some lower boundaries. I should also be aware of this. And maybe even more important than that, I should also know what I would like to optimize. In this case, for example, yield shows itself as the criterion for me, and I'm looking to the values at the final time t. Let's say this is tf, and I have compared to the yield values at the final time t. But there are also several other options, like how these trends are happening here and how they are performing the trajectory trackings with respect to a certain reference value or certain reference curve, and so on. So we have provided a motivational example to you, but the roots of this problem lies in the mathematical formulations, and very well-known mathematicians and physicians worked on this problem for several hundred years, and I would like to briefly mention about some of the most important names here. This optimal control problem basically first initiated with Johann Bernoulli's announcement to the science community, and he proposed a problem which is named as the Berkes-Chorn problem to find the optimal route from a point A to point B in a planar environment. This basically set the initial grounds, and then calculus of variations played a significant role here. So the contributors at that level can be named as the Euler and the Lagrange. So this indicates the 18th century. And then Legendre, Jacobi, and Hamilton created a different type of formalism in order to provide the necessary conditions for the optimality. And this indicates the 19th century. And in 20th century, so Richard Bellman and Lev Pontryagin also contributed to this area significantly. In the next videos of this lecture series, we are going to mention about the Pontryagin's maximum principle in detail. So that concludes this part. In this part, we mentioned about what optimal control is and how it shows itself in practical engineering applications, and provided a brief history regarding with the backgrounds of optimal control and optimal control problems. So in the next videos, we are going to dig deeper into how we can form optimal control problems and how we can solve them in an efficient way.